physics-minded here? Well, since you saw Lenny's talk yesterday, let's move forward with the view that there could be a QMA witness in the beginning of our universe. So what you'll see today could be very useful also from a physics point of view. So we'll start today with QMA and QCMA session, and then next afternoon will be commuting local Hamiltonian session. So let's start with Angelos telling us about QMA and QCMA.
Thank you, Anurag, and the organizers for inviting me. So we're going to start, a lovely Tuesday morning with some oracle separations between QMA and QCMA. Okay, so this talk is going to be, again, tutorial, very high level. I know we have physicists here, so I'm going to try not to be too boring. I'm going to introduce QMA and QCMA and try to motivate oracle separations. Then I'm going to talk about 3 works. The first one, which is from 2007, I think it's very illustrative, so gets some nice high-level ideas. Then I'm going to survey 2 more recent lines of work. So as a computer scientist, one motivating question to study QMA and QCMA is how much more powerful is quantum from classical information? So we all know, qubits live in an exponentially large space, so probably there is something there that we can use, but is this much higher dimension really useful for quantum complexity classes? And so computer scientists have thought of these QMA protocols to study these questions. And let me tell you the protocol briefly. So we have this verifier that's quantum. And it's wondering whether some classical input X is in some classical language L. And it recruits the help of this all-powerful prover that tries to convince that it's indeed in the language. And how do you convince? Well, you can send a quantum state. And then QMA is now the set of decision problems that if indeed X is in the language, then a prover can convince you. They can send you some quantum state, not too large, such that verifier is like, OK, I believe you. X is in L. Otherwise, if the prover, which we don't really trust, what is this hat, is not in the language, is dishonest, then there is no state they can send you such that they can fool you that it's in the language. And so the name is, Quantum Merlin Arthur, and this is, Arthur and Merlin. So one can similarly define a protocol called QCMA, where it's basically the same. Again, Arthur is thinking whether X is in some language and uses the help of all-powerful Merlin. But now Merlin is only allowed to give you a classical bit string as a proof, as a witness. And the same properties hold, right? So if X is in the language, then there should exist a proof. If it's not in the language, then they can't fool you with some proof. So QCMA and QCMA, hopefully I can convince you that it's a fundamental question. So, yes. I'm sorry.
Don't you put like it rejects with high probability?
Sure. This is a high level. Yeah. So I think the definitions are what, 2/3, 1/3. I'm trying not to go into the.
We'll make it 1, but it becomes a different thing.
Yeah.
QCMA actually.
Oh, yeah.
Okay. So QMA and QCMA is a fundamental question. Hopefully, I can convince you. So if you are a physicist and QMA and QCMA are not equal, then that would mean that there are local Hamiltonians whose ground states do not have a useful polycized classical description. And so what do I mean here by useful? I'm not a physicist, so go easy on me. But I mean, the description of here is a Hamiltonian, it's its ground state, is a description. It's not that useful. So we want classical description that allows you to construct this ground state. And that's equivalent to be able to construct it with a polycized quantum circuit. So if they're separated, I guess it says something for problems that we care about. So for computer scientists, as I said in the beginning, we like to study non-determinism in quantum computation, differences between quantum and classical information, and we like to satisfy our curiosity. So this tutorial is about oracle separations. What do I mean by that? So if QMA and QCMA are indeed different, then we cannot really hope to get an unconditional separation because they lie in P between P and P space. So if you separate these two, you're also separating P and P space, and we don't believe we can do that. So one of the things we hope to do is get an oracle separation. So what do I mean by an oracle? Now we're going to have this oracle, which you should think of it as this classical string in the sky. And the verifier, Arthur, again, is thinking, OK, now instead of an input, I have this oracle that's written up in the sky. Is this oracle in this language? Does it satisfy the properties that I care about? And then, again, it uses the help of the prover. And the protocol is basically the same. You are given some quantum state as a witness. And now you can access this oracle using queries. And I guess this is going to be the form of the queries, although I'm going to talk about non-standard oracles. So maybe it's not too, you're not going to see this too much. But basically, you're going to say, I want to query the oracle at position X. And to make it reversible, you have to add this one. So again, before I get into the weeds, for this tutorial, I'm going to survey some recent progress on QMA and QCMA. I already said this, but let me say it. QMA and QCMA is a fundamental problem, and it has been around for a while, and we don't really have satisfying oracle separations yet. But what is good is that a lot of progress has been made in the past 1.5 years. So who knows? Maybe it's time that we resolve this question. OK, so prior work, as I said, it was first posed by Aharonov and Nave in the Quantum NP survey, I believe. Then 5 years later, Aronson and Kuberberg had the first separation using a quantum oracle. So be ready. I'm going to say a bunch of oracles with different names. For now, I'm going to give a brief description about these oracles, but don't pay too close attention to them. What you need to know, I'll tell you later. So what the quantum oracle means here is that it just gives you a black box access to unitary. So instead of a string in the sky, it gives you black box access to unitary in the sky. And we're going to see that it actually has no efficient description. So in a way, it's kind of cheating. I don't know. Then a decade later, Bill with Shelby Kimmel came up with a distributional in-place oracle separation. So in place, I guess, here means that it doesn't satisfy reversibility. And distributional means it has some randomness. Again, don't pay too close attention if it doesn't make sense. Then Anand and Chinmay 2 years ago came up with a distributional oracle. Again, it has randomness in the oracle. Then we joined work with Xingjian, Chipeng, and Takashi. We came up with a classically accessible oracle. Now, it's actually a function on the sky, but you're only allowed to query it classically. So you're not allowed superposition queries.
On your previous slide, what do you mean by no efficient description of the quantum oracle?
No, so it's a high random unitary, the oracle. So this is what I meant. There's no efficient classical description.
But like most oracles, it's true that there's no efficient classical description of them. So it's just because they're like a function in the sky. So what sets this one apart? It's like worse.
Yeah, I guess all of the.
Like even if you allow exponential, usually more description, you can describe it.
So what's the? So
like to describe like a classical oracle, you need an exponentially long string.
Yeah.
This you need doubly exponentially long.
Oh yeah, yes, I guess there's no efficient description.
So the U there is a 2 to the n cubic unitary. Is that correct?
Yeah. Yeah, so it's a unitary. Let's hard on unitary over n qubits.
N cubics. Square.
Okay, so then our work, we allow classical queries. And then recently there's been this follow-up work that extend our result to allow some quantum queries. So you allow some adaptivity, yes, some quantum queries, but there is some limit on the adaptivity. So it's mostly non-adaptive quantum queries.
Sorry, so in this case, it's still unitary, but you've limited the type of query to be classical yet?
No, so for all of these here, the oracle is classical. So it has a classical description. You can write as a string in the sky. For the last two, you're only allowed to access it using classical queries. So for this one also is superposition, but for this one is classical.
Usual model, where you have some oracle in the sky, and then I can also make classical queries to positions in this oracle, right? Like on this exponential long string.
So I don't think I heard the question.
How is that different from the very first model, the old school model?
So for the old school model, you're also allowed to do superposition queries, right?
Oh, I get it. Okay, good. Sorry, I get it.
Okay, so I gave you probably 5 different oracles with 5 different properties. So you're wondering what are all these oracle separations? In the literature, we call those non-standard oracle separations, where standard is the oracle I gave in the beginning, classical function in the sky, superposition queries. And you should take it as a given that this is our goal, obtain a classical oracle separation. It's the most general oracle. It's a little bit more natural than the other ones. So why, 5 different works came up with 5 different non-standard oracles? So I think the story is that you have a team of researchers. They think they have a classical oracle separation. Then along the way, they get stuck on some part of the proof. So we add some non-standard behavior to help us complete the proof that we don't know. And hopefully I can, actually, let me say this first. So in all of these 5 different oracles I said, they actually do one of 2 things. You either restrict the prover to give you one type of witness, so we can show that they can't fool you, or you restrict the access to the verifier to make it easier to prove a lower bound. Lower bounds are usually harder to show. And actually, Bill with some co-authors showed that gave a task whose quantum complexity actually changes significantly if you play around with the oracle a little bit. So you have to be careful with these non-standard oracle separations. And of course, you have to be, scrutinize every result. But hopefully what I can tell you and convince you of in this talk is that these results actually say something meaningful, and it's something that we really believe gives a classical oracle separation. And we just got stuck in some technical, let's say, details, maybe not details. And that's why we introduced the non-standard oracle. And who knows, maybe an actual separation arrives from one of these.
All the oracles to be potential candidates. There's no reason.
I don't want to make a formal statement here, I'm just a grad student, but...
If you stop the recording, you would say that.
Wait, we're recording? Okay, maybe I shouldn't have said that. For me?
I have an annoying question, but is it always clear that you want a classical oracle separation over any quantum oracle separation? I could imagine you have a classical oracle separation relative to some really crazy classical oracle that's totally uninstantiable, versus quantum oracle separation relative to some unitary that is actually instantiable, maybe instantiable with a pseudo-random unitary. Would that actually be much worse? If one oracle separation is more easy to translate to the standard setting where there's no oracles, is classical always better than quantum?
So that's a good question. So if you take, so Fermi's question just to rephrase it is that, is it clear? Basically, I told you take it as given that the standard oracle is the goal here. And so honestly, it's unclear. I think you bring some pretty good points. The question is your goal really to instantiate the oracle? Right? I mean, this is kind of a theory setting anyway. So if your goal to instantiate the oracle, if your goal is to instantiate the oracle, then maybe you have to be a little bit more fine-grained. But I mean, also, yeah, I guess it's more general. And yeah, that's what I would say. I don't know if I have a super satisfying now. So if you wanna, I was gonna complete the thought. I was gonna say if you wanna. So for example, the oracle of QMA and Anand, you can maybe stretch a little bit to think of it as a sparse Hamiltonian, which may not be something you can do with other non-standard oracles. So maybe a more general classical one is easy to be useful.
Yeah, maybe actually on your list, no, you don't move, but on your list of why you want a classical, why you want an oracle separation. I think one of the main reasons you want that is to show that if you had a proof that collapses, in this case, QMA to QCMA, then if you had a proof, that proof must not relativize.
Oh, that's actually a good point, yeah.
I'm not sure that you get this from these non-standard oracles, you get the conclusion, which I don't know. But for sure, from the classical one, this is the conclusion you can draw. And I think that's the main reason why you want an oracle.
Isn't the word like relativized just like defined with respect to classical oracles? Though, like we could define
Yes.
the notion of relativized for all the other oracles, right? So
Yeah, I was wondering what that means actually.
I think relativized just means like still holds relative to any classical oracle.
Right.
So, but I'm saying like
Which
that
means
word
that
is
the
like
proof, and most of the proof techniques we have don't relativize. So it
So-
means that you need some non-standard proof technique to show that it's conclusive.
right. But I guess have people looked into the word relativized defined for other kinds of oracles? Like
But basically, that was my question.
Oh, okay.
And then if that doesn't work, then the reason why you want the classical one answering your question
yeah, yeah.
is because it gives this conclusion.
Scott has some stuff about quantumly non-relativizing
Yeah.
stuff, so relative to a quantum oracle. As for like the more recent non-standard oracles, I guess too soon.
So the one I had in mind is in the 2007 paper with Kuberberg, they tried to make this argument that the quantum oracle, you can only break it with a quantum non-relativizing approach. And we don't know of any quantum non-relativizing approaches that are not also classically. So in principle, if you find something that breaks the quantum oracle, then I guess it's weaker, but they don't have one. I don't know if that's still the case. Maybe there is still a technique now that it's quantum non-relativizing. Yeah, so this is kind of why I said take it as a given, because, yeah. Sorry.
So what do you mean by most general oracle?
So what I meant here is for in the distributional oracle case, for example, you want distribution over oracles. So a deterministic oracle is itself a distributional oracle, right?
Functions are not reduced.
I mean, you can think of a unitary that's over basis vectors, right? Yeah, but I guess Fermi brought up a good point that maybe instantiating the quantum oracle itself is different than, it's harder than a classical oracle that's different. Anyway.
What do you mean instantiating?
Yeah, so typically, it's probably something from cryptography. People like their, yeah. You like to have a random oracle and then instantiate it with something real world. Okay, so then, yeah. So it's a long discussion. Just to review, hopefully I can convince you that these non-standard oracles here are actually useful and hint towards a complete solution.
So if you could instantiate a random Berkeley separation into a hash function, let's say, would that lead to a Hamiltonian? Like, can you do Cook-Levin on these things? So could you say like QMA and QCMA as your cryptography or something like that? Like, does it make sense?
The prover could just tell you the key that you use for the hash function.
I see. So instantiating is not useful at all. So
Well, okay, so my
What's your question?
the question is that it doesn't make sense to instantiate these random oracles with a hash function, and could that lead to local Hamiltonian assuming cryptographic assumption, which would witness QMA versus QCMA? And Chinmay said, no.
Whenever I get lost in thinking about these oracles, I think about the simplest oracle, which is like the P versus NP oracle separation, which is just you have a long string, which is all zeros, except there's a one perhaps somewhere, right? Unconstrained search. And why do we use this oracle? Well, it's supposed to simulate that for a SAT formula, effectively being described as SAT formula is no better than just being able to only evaluate, right? So the oracle is supposed to sort of take an object which has some compact description, which you believe any access model, any computational efficient access model, would effectively just have exponential complexity, and you just force that. So you don't worry about the prover being able to like break it inside there. It just like similar, what it proves is that P versus NP or like BQP versus NP, the only way they'd be equal is if you look inside the SAT formula, right? You have to look inside, and effectively in these oracle settings, it says you have some complex string, you have to look inside the structure of the string, right, in order to figure it out.
So generally, there is a love-hate relationship with oracles, as you can see. Okay, so moving to the quantum oracle separation, that's going to be, I think, the most illustrative one. So the statement is that there exists a quantum oracle, so unitary in the sky that you can query, meaning send the quantum state and it's going to give you back psi, such that QMA and QCMA are different. And then this is the QMA protocol that I described before. So now we are wondering if this unitary in the sky is in this yes instance. And what is the yes instance? the yes instance means that it's unitary such that it acts as identity on almost everything, but it reflects this random secret state psi. And otherwise, I promise to you that it's going to act like identity on everything. So, I mean, how would you convince me that there's a unitary that preserves everything but only reflects one state? You kind of have to send me the state, right? There is no other way. And this is, OK, I have the task again. So the yes instance it's a unitary that only reflects this random secret mark state, or it only acts as the identity. And let me convince you that it's in QMA. As I said, you can send this marked state psi, and then I can compute and check that it's reflected. And how do we show that it's not in QCMA? Well, basically, unless the verifier somehow gets a hold of this quantum state, any query you make to the unitary, it's going to have very little overlap with this psi. So it's going to act like the identity. And well, if it's act like the identity, this is both yes and no, so you can distinguish. But you actually need exponentially many classical bits to describe this random state. So classical witness is not going to be useful.
So in this case, you don't have to describe it, right? Calculate the action.
So you want to make the verifier construct psi.
Oh, I see.
Right? Because then it's going to, otherwise, any query you make to the unitary is going to act like an identity. OK, so that was the warm-up. Let's go to the distributional oracle separation of Anand and Chinmay. So the statement is that there exists a distributional oracle that separates QMA and QCMA. And this is going to be a classical function in the sky that has randomness. And what's the problem? The problem is going to be expanded distinguishing. I'm going to give you an exponentially large graph. And it's either going to be, in the yes instance, many connected components. In the no instance, just one connected component. So many of you are going to ask, how do you encode an exponentially large graph? You're going to see at the oracle slide. What else do you know about this graph? You know that in both instances, again, exponentially large, they're going to be regular. Actually, here, they're not irregular, but whatever. And the degree is going to be constant. So sparse graph, random looking, and also all of the components are going to be spectral expanders. So both in the no case, it's going to be an expander. Both in the yes case, even though it's disconnected, this is an expander, this is an expander. Should also say it doesn't have to be only two components. It can be 2, 3, up to 100. So the oracle, as I promised, how do we encode this exponentially large graph? Well, it's going to encode the adjacency list. And so I colored the edges here to make it easier to see. But basically, you're going to give us input to the oracle, a vertex, and then something that identifies the edge. So here is going to be the color for visual. And it's going to give you the neighbor that's adjacent to that edge. So for example, here, you can ask, what is the red neighbor of V1? And it's going to give you V2. And that's a valid reversible operation because the red neighbor of V2 is V1, right? So if you apply twice, you get the same thing back. And looking forward, this oracle, the way it's like that, it allows us to run this phase estimation to estimate eigenvalues of the adjacency list matrix. OK, let me convince you that expanded distinguishing is in QMA. We have yes and no instances on the right. So observation number 1, the second eigenvalue of the yes instance is 1. It's disconnected. So there is the one eigenvalue of the uniform distribution over all of the vertices. And it's disconnected, so there is another one eigenvalue. However, recall I said all of the components are spectral expanders. And because this is connected, its second eigenvalue is bounded away from 1. So it makes sense now to consider maybe the witness will be the eigenvector that corresponds to the one eigenvalue of the yes instance, right? And let's see this a bit more in detail. So as I said, there is one eigenvector that has eigenvalue 1 for both instances. That's just the uniform superposition over all of the vertices. And in the yes instance, we have another one eigenvector. Doesn't matter exactly what it is. It's just some combination of vertices in the left and the right, and also they're perpendicular, the first and the second eigenvector. Whereas in the no instance, every perpendicular eigenvector is going to have an eigenvalue bounded away from 1 because of the spectral expansion. So I wrote these observations at the top to remember them. And here is the QMA protocol. The witness is going to be psi 2. And the verifier will do 2 things. You first check that it's perpendicular to the first eigenvector. And note that this first eigenvector is always the same, right? It doesn't depend on the exact structure. It's just uniform superposition over the vertices, which is the same for both yes and no. And then we're going to check that psi 2, the witness, is a 1 eigenvector. This is going to be done with phase estimation, which, as I briefly argued before, can be done using the oracle. And that concludes expanded distinguishing is in QMA. So why is it not in QCMA? Let me rephrase the goal. So if I give you a classical witness of this graph, this very large graph, then you need many queries to the adjacency list oracle to distinguish one from many components. So here is the plan. We're going to assume the witness I give you has some specific form, which is subset witness. Then we're going to prove a lower bound for this specific form. And then we're going to remove this witness assumption. We're going to boost this result from subset witness to general witness. Okay, I'm going to say it again. So proof over U, assume it's a subset witness. What is a subset witness? It's a witness that only depends on the vertices of the components. So in the yes case here, you can only give me a witness that knows about S1, what vertices are here, and what vertices are here. It cannot know the exact edges inside here, just the vertices, just the subset. And then we're going to prove a lower bound for the subset witness. This is the main technical contribution. It actually has some very nice results in there. And then we're going to remove the witness assumption, which is what we're going to focus on here. And this is where we're going to need the distribution and oracle. This is when I said the part of the proof we don't know how to do, and we're going to use the oracle to fill it in for us.
If you want to prove that this is not in NP, is it possible with standard oracle?
If you want to prove this is not in NP, I don't know how much that one is easy.
It's just QCMA.
And given the witness, then the queries are fixed, right? And then I think you can construct an all instance out of it because you know exactly what the query should be, right?
I see.
I would say that something that should work.
So it should be easy to at least roll out NP.
Well, actually, the triangle distinguisher should still work. No?
That's average case.
Yeah, but I mean, okay, anyway, unclear. Make unclear to me. So back to the, to the talk. So distributional oracle here. So far, I have hopefully convinced you that the expanded distinguishing is not in QCMA if the witness has this particular structure. So it turns out it's actually not too easy to show a lower bound if the witness can depend on the edges. And I'm going to show in a little bit a nice triangle distinguisher that works, an average case, but you still somehow need to rule it out. So how do we show that even if you have the edges, it doesn't matter? Well, don't allow the prover to see the edges. And what do I mean? This is how the oracle is going to go. There's going to be a phase 1 where the vertices only of each connected component are revealed. So if it's a yes instance, you only see these. It's a no, you see the whole thing. Then the prover will see this, all powerful, will compute the witness. It sends it to the prover. And then in phase 2, the edges are chosen from a distribution, and now they're fixed. They're not going to be sampled again. And now the verifier, given the witness, can query the oracle, and it's going to see what it's going to see. So now, I think it makes sense. The prover doesn't have any access to the edges, doesn't know the edges. It only knows they're going to satisfy the connected components. So it will have to depend on the vertices, thus a subset witness. So as I said before, this distributional oracle forces a specific type of witness. And you may ask, okay, how much power do the edges give to the witness? Did we really have to do this? And in the quantum witness, we actually didn't need the edges. We only needed the subset of the vertices. But actually, the edges can actually give you a lot of power. And this is the triangle distinguisher I promised. And this is actually due to William. Basically, so this is an average case. Let's say we have these graphs. And I promised to you that they're random graphs. So the edges are chosen at random, conditioned on the number of the degree. So it's not too hard to show that the expected number of triangles is d cubed, where d is the degree, times the number of connected components. But in the yes case, you have 100 components. Here you only have one. So the number of triangles you expect to see here is 100 d cubed. Here is just d cubed. And d is constant. So here you expect to see, I don't know, 1,000. Here only 10. So the witness could be just a list of triangles. It's a short one. And yeah, in no instance will have less than 50 d cubed because the expectation is much lower. And yeah, so this may give us a pause. I tried to convince you that this subset witness is a good assumption, but I just gave you a classical witness that can solve expanded distinguishing. So, and it uses crucially the edges of the oracle, right? It uses the triangles. So first thing is that this is over a distribution of graphs, right? You could actually sample graphs that do not have any triangles. So, okay, we can solve that. However, maybe there is some other property of the edges. Okay, if you remove the triangles, now I can start counting 4 clicks, 5 cycles, whatever. So this actually highlights a big obstacle towards getting the classical oracle separation. You somehow need to show that there is no edge property that is going to help you distinguish one from many connected components. So here it was triangles, but could be some other very weird property. Yeah, so this is why we somehow need to show this, and this is where the distributional oracle comes in. So as a summary, we believe that actually expanded distinguishing is not in QCMA with a classical oracle, and the distributional oracle just fill-ins the proof that we do not know. Okay, I think I only have 10 minutes, right? Okay, I think we can make it. Everyone back collab. Okay, so there's a second line of work that follows some different techniques. Actually, sorry, let me actually stop, pause for questions. Doesn't matter that we go through it. If you have questions. Okay.
So how does it to restrict to having no small cycles or no triangles?
So it's not too hard, right? This is, I mean, I didn't do this, right? It's QMA and QCMA, but you can show even with a distribution over, random graphs, it's only a constant fraction of them that don't have triangles. The expectation is not too high. So you can do it kind of a black box, just say sample, and then if it has a triangle, you read it. Yeah, so it's unclear as the things get more complicated, the analysis gets a bit hard.
So, so if you knew that there are no small cycles or triangles, is there a way to prove things? Assuming, so what is the main bottleneck there?
So the main bottleneck is that generally, if it's not triangles or small cycles, there could be some other combinatorial structure of the edges. We actually had this discussion yesterday that it has to be at most log size, right? I think logarithmic size. Yeah, but
that's it's not clear. It's not clear if that's sizes.
Yeah. I mean, I don't know. Do you have any?
Okay, correct me if I'm wrong, but I think like even if you allow for general witnesses depending on the edges, like I think the NP lower bound should be doable, but I don't know how to show that even this comes on an MA. It shouldn't be an MA, but I don't know how to prove it.
Mm-hmm.
So maybe that's like the first step towards showing this general
Okay.
QCMA.
Okay. So then, just MA means no quantum queries.
But
Okay.
you have randomized queries.
I see. So you're giving me a very nice leeway towards the next step of the talk also. Okay. Yeah, so maybe a nice first step would be, can we show this even without any quantum queries? Okay, so then the second line of work, which I'll be very brief and very high level, is restricting the oracle access. So what I argued to you so far is that the prover now doesn't see the whole oracle, so they restrict the witness. Now we're going to restrict the verifier to make it easier for us to prove the lower bound. And this is, I guess this is from our work in 2023, where we restricted the oracle to be classical access. And some very exciting recent work by Ben David and Kundu showed that you can actually get quantum queries, but they have to be non-adaptive. So I don't know, take it as you want. Is it closer, almost there? I don't know. But yeah, pretty good. Things are happening, so maybe a good time to think about these problems. Okay, so I'm gonna be brief. So our construction draws from the Yamakawa-Zandri problem and some follow-up work by Chipeng. And let me give you a very brief warm-up. So let's say our oracle problem now is asking the verifier to distinguish an all ones oracle from a third ones. So it's either all ones or few ones. So this is easy, right? You don't even need any witness. You can just randomly sample. If you see at least a 0, you're going to distinguish. So the idea now is that we have this very easy oracle. We're going to embed it into this much bigger oracle. So imagine this exponentially bigger. And we're going to place the contents of this oracle into these positions here. And the trick is that going to be these positions are going to be hard to compute. So this I3, this IK, it's going to be really hard to compute. It's like a desert, and you only have a couple of useful information here. So then the question is, OK, sure, where are you going to find these hard instances, these hard indices? So then the slides are given. Anyway, so we want to distinguish whether in this huge oracle with some values here, we either have all ones or there is mostly zeros. And then, as I said, most of the oracle is going to be empty or garbage. And the places where we place the information are going to be hard to find. And where do you find these indices? They're going to be the solutions to this Yamakawa-Zandri problem. So I'm going to very briefly describe Yamakawa-Zandri. So Yamakawa-Zandri showed that there is a function relative to a random oracle that you can invert on any image T if you're given quantum access to the oracle H, but you cannot invert on any image if you're only given classical access. So in images, this is how it looks like. So you have this function f, and you want to invert on T. It has many preimages, but you can only invert if you're given quantum access to this H. This H determines f. So Chipeng then realized that actually you don't even need access to H. The access that you need is very limited. You actually only need some state, which we call an advice. So actually what he showed is that, again, you don't need any queries here. If I give you a quantum state that depends on H, you can still invert. If I only give you a classical bit string, no matter how it depends on H, you cannot invert. So then the first thing we did is that we extended this to say that, well, now, let's go to the picture. So now, even if I allow you to get classical queries to H, and you have a classical advice for this oracle, you still cannot invert. Whereas if you have a quantum state, plus quantum queries, you don't need them, but even if you have them, you can invert.
Sorry, I have a very basic question. What do you mean by invert if the domains are different? Do you mean you get all of the things?
Just any one preimage, any one preimage, yes. So any one of these V, it doesn't matter. So going back to the thing I told you, we have this small oracle of either all ones or mostly zeros, and we're going to put them in these positions, and these positions are going to be indexed by T, V pairs that are image and preimage of the Yamakawa-Zandri function. And so I want to make this point clear here that we actually have two oracles, right? There is this O that we are accessing, but this function of Yamakawa-Zandri is defined based on this H oracle here. But this H is nowhere to be found, right? You don't have access to it. It's implicitly defined through the function, but it's not there. And so the name of the game here is to actually learn about H so you can invert and find the useful positions to query. OK, this is how it schematically looks. There is no H here. So how are you going to get the H? Well, it's going to be in the witness. So let me convince you that the language is in QMA. The witness is going to be, as I said, the quantum state that allows one to invert FH. You don't need to have any access to H, just the quantum state suffices. And so the verifier, what's going to do, it's going to sample some random image. It's going to use this witness to invert F. And so now it has obtained a valid index that has useful stuff. you're gonna query. If you see a 0, it's a no. If you see a 1, it's a yes. So let me convince you that it's not in QCMA. Well, actually, basically you can only distinguish if you query at the valid coordinates where they differ, right? And as I said, these coordinates are actually hard to find. They're solutions of the Yamakawa-Zandri problem. So you can only distinguish if you query at some t, v. And recall that we actually said that it's hard to distinguish if you have classical advice. It's hard to invert if you have classical advice, and you're only allowed classical queries to H. So this is kind of where the classical query restriction comes to. You need to have classical queries. So I think, yeah, let me briefly say why we need to restrict the access to classical. So the name of the game, as I said, is to learn some information about H through querying O. So we argue that classical queries to O leak very little information about H. And this is part of the main lemma that I showed here. And this actually doesn't hold, with quantum queries, because if you have quantum queries, Yamakawa-Zandri said, you can actually invert. You don't even need advice. And so we didn't know how to argue that quantum queries do not allow one to simulate quantum queries to H that allow you to invert. So this is why we get the oracle, and we require only classical queries to the oracle to fill in this step. So then what is nice is that in the follow-up work, Ben David and Kundu showed that you actually can have quantum queries to O, and they will also leak very little information about H, as long as they are non-adaptive, or mostly non-adaptive. You're allowed some log rounds of adaptiveness. Yeah. And I mean, the big question is, can we push this further? Can we get fully adaptive quantum queries?
So is there a connection between this oracle and the Gemini and oracle? Like, at least in the QMA part, it seems like there's already a difference. There's no phase estimation in your case, but there's phase estimation in their case.
Mm-hmm.
But is there a view on them which is more broad, more defined from this QMA perspective?
My first response would be, I think no, because you see also the different queries that the different oracles that we have. They restrict, one of them restricts the prover, the other one restricts the verifier. So yeah, maybe my first reaction would be, maybe we're approaching the same problem through different ways. So maybe we can learn something from each other. Yeah, but I can't really see too much similarity. So this concludes the talk, right on time. So yeah, the oracle separation does remain open. I think we have a number of avenues that could be useful. And yeah, a lot of progress in the past few years, so probably a good time to think about this problem as well. And then obviously the big question here is, can we get a standard oracle separation, right? Can we get the classical one? So also, in the beginning, I glossed over it, but I said we can't hope to get an unconditional oracle separation. So we're going to get an oracle separation. But maybe we can also get a conditional one. So there has been some work on showing some structure of QMA witnesses and how you can compute them. So maybe we can say, if BQP is different than some other class, maybe we can then also separate QMA and QCMA. As far as I know, it hasn't been studied too much. So it may also be a fruitful avenue to think about. So that's the end of the talk. Thank you all for listening, and I'm happy for more questions.
More questions? Right.
So is there any plausible way that you see to spoof a quantum state whatsoever with the classical, or is it it's pretty clear the difference and it's unspoofable?
So when you mean spoof, you mean, what do you mean by spoof?
Convince that you basically act like you have a quantum state, but you actually don't have a quantum state. You have a classical state that has a similar structure to the quantum state.
So I don't know if this is exactly what we're trying to do by the oracle separations, though, right? It's not about the prover trying to convince you that they have a quantum state. It's about giving you the recipe to construct on your own and then verifying. So even if you can spoof some states, which there's many states that can be classically scalable. Maybe there is quantum states that are useful, and you actually need inherently quantum description for them. Yeah, did I understand your question correctly?
I have a physicist question. Before we get to oracle separation, I should expect these two classes to be different. Is that the CS expectation?
So this was my expectation. I have to say I was recently reading the original Haronoff-Nave paper, and I think they were saying that they expect it to be the same. I don't know, maybe I misread. Is anyone?
Yeah.
So, I mean, if the expert, okay, probably it was 20 years ago, so maybe they updated their prior. But I guess there is surprising classes have collapsed before. So unclear, but I think people believe they're different.
So it almost feels that this last oracle that you described works. But we don't know how to show that it works by getting rid of the adaptive. Is that correct? Or do you think it actually doesn't work when you have adaptive quantum theories?
So I think for all of the oracles, they don't obviously fail. So if you try to get a classical oracle one, they don't obviously fail. So yeah, I think. Sorry.
But in the quantum, I don't know what that means even in the quantum oracle to make it classical.
Oh yeah, actually, so I didn't mean. I meant the last two. Sorry, I meant the distributional one and the classical access one. There is no obvious thing that makes them break. So if we believe whether they are true or no, I think it's subjective. So for me, I think after they obtained this, after the follow-up work of kind of mostly non-adaptive quantum queries, I guess confidence has increased that you can do something, but still unclear, mostly subjective. I think though they do bring up some good ideas, both oracles. So maybe there's something to learn from them. And even if it's not the exact oracle construction, maybe something related works.
Okay, so maybe we take more questions offline, and we'll take a break and come back at 10:55.